So the solutions to the physics classroom type force homework problems. So the first one was number 13. It was kind of all by itself as a problem set. This is very similar to one we did in class. So the key thing here, I think, is drawing out the picture, thinking about this triangle, because the tension is at an angle, and you want to think about the fact that the vertical component of the left wire and the vertical component of the right wire are what's going to equal the force of gravity down. So you need to figure out the weight down, which is m times g. So that's 43.1 kilograms times 10 newtons per kilogram, 431 newtons down. So what's holding that up? Well, these wires are holding it up, but they're also pulling against each other. So we need to figure out, again, the vertical component of the wires, and then we use that to figure out tension. So each wire's vertical component would be T times the sine of this angle. So that gets you this side, and because there's two wires, we add it twice. And so then I can say 2T times that sine of that angle is equal to 431 newtons. That's the trig going through, so it's about 380 newtons of tension in each cable. So I worked my way back from the vertical force, which I figured out, in order to figure out the tension force. For the first three problems here, 1, 6, and 7, those are pretty straightforward. So for an elephant, you're just converting mass to weight. On the moon, the gravitational field strength is different. The mass does not differ elsewhere in the universe, but the gravitational field strength does. So I divided the total by 6. It got me 10,000 newtons. For P6, we're looking to find the net force on the person and the gee whiz, which is the rocket sled. So we use the total mass multiplied by the acceleration that was given and got the force that way. Notice the pattern I've got. General formula, numbers plugged in with units, final answer with units. 1, 2, 3. General formula, plug in numbers with units, final answers with units. 1, 2, 3. Here I did it all at once. For number 7 here, it's basically asking to figure out the acceleration. So I use Newton's second law, but I rearrange that to solve for acceleration. Net force, Sophia's mass, Sophia's acceleration. Going to look at the last four. For problem 14, this is first thing would be the free body diagram. So the gravitational force down is equal to the normal force up. I can figure that out. Well, actually, that was given. So I've got the pull and the friction force. So the pull has got to be bigger than the friction force, obviously, in this case, and so the sled's going to accelerate. So if I want to figure out the mass, I'd rearrange this equation, which is one of the three we've been talking about, to solve for that. The net force, I simply subtract them, and then the acceleration is net force over mass, so 28 newtons divided by 30.4 kilograms. For problem 17, this is a problem with air resistance, which we looked at in class. So at some point afterwards, before terminal velocity, gravity is greater than the air resistance, but there's still some of each. So the gravitational force, which is the same thing as the weight, I can simply use mg. So general formula, plug in numbers with units, final answer with units. Gravitational force is 825 newtons. Here, it said that the air resistance force was 118 newtons. So if I think about separating the gravitational and air forces out, I can get a net force. So 825 down, 118 pushing up. Mass I had figured out earlier, so it gives me around 8.6 meters per second squared. As the person falls faster and faster, gravitational force won't change, but the force of the air resistance will change. That means the net force reduces, and the acceleration will reduce. For problem 21, what we end up having is it's a rocket accelerating upward. So I should have drawn a free body. Oh, I did draw a free body diagram over there. The thrust upward and gravity downward. It gives me the mass. It gives me the acceleration. So the net force has got to be 4.77 newtons up. But since that's the net force, the thrust actually has to be significantly larger than that. since the mass is acted on by gravity downward. So I separated this force into the two forces acting on the rocket. Thrust minus gravity equals m times a. So I figured out the gravitational force by multiplying m times g. And then I did the thrust minus that m times g. So I did T minus 1.04 newtons is equal to, actually in this case it would be, again, the net force up, so that's 4.77. So I basically add the 1.04 and the 4.77, end up with 5.81 newtons. Problem 26, I smudged. Problem, why did I call that 26? Oh, it is 26. Ended up getting the mass of Mr. Spring, the acceleration of Mr. Spring. I figured out his weight in this particular case, so just m times g again. The coefficient of friction was given. First thing was to draw the free body diagram. The second thing was then to figure out the net force. Well, if I know the acceleration is mass, I can get the net force. Third thing, and I guess that here, the force of friction is coefficient of friction times the normal force. But we know the normal force and the weight are going to be equal thanks to that free body diagram. Finally, the pushing force minus the force of friction should give us the net force. So end up having the net force is equal to push minus 294, so therefore the net force is around 395 newtons. So hopefully those make sense. I know I might be forcing it. Ha! That's a pun. But we do have our test tomorrow. Or actually, because I'm recording this the day before the test. So we do have the test on October 30th, and hopefully you'll look over these, maybe come to a review session, and do well.